All right, today we're going to go on a pretty wild journey. We're starting with something you'd find on any beach, a grain of sand, and ending up inside the supercomputers that power our entire world. We're going to unlock the secrets of semiconductors, those tiny, incredible engines behind basically all of our modern technology.
So it all really comes down to this one kind of mind-blowing question. How on earth do we take a simple rock, silicon, which is basically just purified sand, and turn it into the brain of your smartphone? I mean, it feels like it should be magic, right? But it's not. It's just some seriously cool physics.
So, to figure this all out, we're going to build our understanding from the ground up, piece by piece. We'll start with the real basics of different materials, then we'll dive into the atomic physics that makes it all tick. After that, we'll see how we can actually hack these materials to do what we want, and then use them to build the most fundamental components in all of electronics.
Okay, first things first. To really get what a semiconductor is, we need to know where it fits in the grand scheme of things. Just imagine that every material in the universe exists somewhere on a spectrum, and that spectrum is all about one simple thing: how well it lets electricity flow.
So on one end of the spectrum, you've got metals, like copper. Think of them as a massive multi-lane superhighway where electrons can just zoom along freely. These are your conductors. Then, way over on the other end, you have insulators, like rubber or glass. They're like a solid brick wall. Electrons hit it and just stop. They can't get through. And right there in the sweet spot in the middle, that's our hero, the semiconductor. It's not a highway and it's not a wall. It's more like a toll road, where we have the power to open or close the lanes whenever we want.
So what really makes a highway different from a brick wall when you get down to the atomic level? Well, the answer is all about something called the energy gap. And to make sense of that, let's just imagine for a second that atoms are like tiny little apartment buildings for electrons.
Now, in our little apartment building, most of the electrons are hanging out on the ground floor. It's crowded, it's where they're supposed to be, and they're pretty much stuck there, bound to their atoms. In physics, we call this the valence band. It's just their normal resting energy state.
But for an electron to actually move around and create an electrical current, it needs to get up to the top floor of the building. Up there, there's tons of open space to roam free. This free movement zone has a name, too: the conduction band.
So, how does an electron get from that crowded ground floor to the empty top floor? Well, it has to climb a staircase. And the size of that staircase, the amount of energy it takes to make that jump, is what we call the forbidden energy gap. Honestly, this gap is the single most important idea to understand all of this.
And this right here shows you everything you need to know. For metals, the ground floor and the top floor, they overlap. There's no staircase at all. Electrons can just wander into the conduction band whenever they want. Now, for insulators, that energy gap is massive. The staircase is like climbing a skyscraper. It's practically impossible for an electron to make that jump. But look at semiconductors. The gap is small. It's a climb for sure, but it's a totally manageable one.
You know, a pure semiconductor by itself is like that toll road with all the booths closed. It's kind of neat, but not very useful. But this is where we get really clever. We can fundamentally change it. We can hack silicon through an incredible process called doping.
Doping sounds really complex, but the idea is actually genius in its simplicity. You start with an unbelievably pure crystal of silicon, and then you intentionally sprinkle in just a tiny amount of atoms of a different element. And that tiny addition of what we call impurities completely rewrites its electrical personality.
So, here's the crucial part. You can dope it in one of two ways. It really all comes down to how many electrons the impurity atom has in its outer shell. A pure silicon atom has 4. Now, if you mix in something like arsenic, which has 5 outer electrons, that 5th electron is just kind of left over. It becomes a free-roaming negative charge. We call that N-type, for negative. But if you add something like boron, which only has 3 outer electrons, you create an empty spot, a hole, where an electron should be. This hole acts like a positive charge, and we call that P-type.
Okay, this is where the real magic starts to kick in. What do you think happens when we take a piece of our P-type silicon and stick it right next to a piece of our N-type silicon? Well, we create the absolute foundation of all electronics, the p-n junction. The absolute instant they touch, all those extra electrons from the N side rush over to fill in the empty holes on the P side. This creates this really thin, electrically neutral zone right at the boundary called the depletion layer. And this layer is key because it has no free charges and it acts like a barrier, stopping any more electrons from trying to cross. But we can control this barrier. If we apply a voltage,
say connecting the positive end of a battery to the P side and the negative end to the N side. We're basically pushing the electrons and holes toward each other at the junction. This shrinks that barrier right down. The turnstile swings open, and bam! Current flows right on through. We call this forward bias.
And you can probably guess what happens if we flip the battery around. Now we're connecting positive to the N side and negative to the P side. This yanks the electrons and holes away from the junction. That barrier gets wider and wider, the turnstile slams shut, and pretty much no current can get through. Just like that, we've created a perfect one-way street for electricity. And this little device is called a diode.
So a one-way street for electricity is amazing, but what if we could do more? What if we could not just direct traffic, but turn a massive flow of traffic on and off with just the lightest touch? Well, we can. By sandwiching these p-n junctions together, we create what is arguably the single most important invention of the 20th century, the transistor.
A transistor is really just a semiconductor sandwich. You can have an N-type layer squished between two P-type layers, or, more commonly, a P-type layer squished between two N-type layers, an NPN transistor. It has three connections, one to the emitter, one to the collector, and one to that super thin, lightly doped layer in the middle called the base. And this simple sandwich design gives the transistor two incredible superpowers. First, it's a switch. A tiny little trickle of current into the base allows a much, much larger current to flow from the emitter to the collector. No current to the base, and the main flow is turned off. Second, it's an amplifier. A small change in the base current creates a huge, identical change in the main current. It's like using your fingertip to turn a faucet, and that faucet controls a giant fire hose.
So, now we have it. A microscopic, lightning-fast switch with no moving parts. What can we do with that? Well, by saying that on represents the number 1 and off represents the number 0, we have just created the physical building block for all digital information. This is the leap from physics to computation.
Now we can start combining these transistor switches to create simple decision-making circuits. We call them logic gates. For example, an AND gate is a little circuit that will only output a 1, or on, if its first input and its second input are both 1s.
An OR gate is a little different, a bit less strict. It'll give you a 1 on the output if its first input or its second input is a 1. Pretty straightforward, right?
And then you have the simplest one of all, the NOT gate, sometimes called an inverter. And it does exactly what its name suggests. It just flips the input. You put in a 1, you get out a 0. You put in a 0, you get out a 1. And that's the whole story. From understanding the physics of the energy gap, to hacking silicon with doping, to building one-way diodes and tiny switches, and then arranging those switches into simple logic gates. By combining billions, literally billions of these simple AND, OR, and NOT gates, we have built our entire complex digital world. It really makes you stop and wonder, what's the next fundamental building block going to be?